evaluations and the like. Yeah, where did we stop? We stopped with basically discussing for here our first the investment project, which was comprising of basically depositing money at a fixed interest rates of 5% in different times. In different points in time. So we started with the $300 additionally, then we had additional $400 in period T1, and then additional $500 in T2, and then we introduced you into these two ways to calculate basically the time 3 future value, meaning the value of this stream of cash flows in period time T. The sequential approach would have been that we sum up across different periods the value of the cash flows, meaning we would take the 300 with the interest to the next period, sum them up with the 400, which would give us 700 something euros, and we would take them to the next period, T2, and then take the sum of the 700 and a little more with the 500, and then calculate the future cash flow value in time period T for the summed value. That was the one approach. The other one we discussed, we would take each one individually, each of these investments amounts, and simply say, what is the future value in period time 3 of the 300? What is the value of the future value of the 400 in time 3? What is the future value of the 500 in time 3? Importantly, this should give us the same results. Good. Next period, and here comes more, we get more of the form of like an investment period where you have upfront costs. So suppose we have a project which requires upfront 1,500 in period T0. Afterwards, in the subsequent periods, the project generates a positive cash flow of 500, 1,300, and 2,000 at times 1, 2, and 3, respectively. Right? The discount rate is 12%. And now the question is, what is the project value as of time T equals 0? First question is this a discounting or a compounding problem? As described here in the question. Discounting or compounding?
Discounting.
Exactly. And why is that? Just to also remind all others, why is this the case? Why is this a discounting problem?
Because we move the investment to the past or move back.
Exactly. Yeah, exactly. Because we basically have here future payoffs and we're interested in what their value is when we discount to a previous period, meaning here in our example where we discount it to our present value at time T0. Perfect. First question. In which time do we have to plug the 1,500 on our timeline? Well, it's already mentioned here in the point, right? So in period T equals 0, we have to plug the 1,500. Question, 1,500, would we write here really 1,500 or what would we have to write here? Would it be 1,500? Or would it be something else?
I think it is minus 1,500 because it is the cost we have to pay at that time. So it would be negative as recorded in the cash flow.
Exactly. Perfect. That's exactly what is the case, right? We have upfront cost. So in terms of cash, well, you have upfront cost in the amount of 1,500. Well, these 1,500 you do not get as a firm, but you have to give them to someone, right? Who will provide you then some service back. But in terms of the cash, well, you have an outflow of 1,500 in T.0. And after this initial upfront cost of 1,500, the project then generates positive cash flows of 500, 1,300, and 2,000 at times 1, 2, and 3. So in point 1, we would have what amount here? We would have 500, exactly. 500, not minus 500, because, well, after the initial minus 1,500 investments in period T1, we would obtain 500 plus 500 units. In period T2, we would obtain 1,300. And in period T3, we would obtain 2,000. So just if we take a look at the cash flows in terms of the timeline, that's exactly what we see here. We have initially minus 1,500 in T0, then 500 in T1, 1,300 in T2, and 2,000 in T3, right? And now the question is, we have to move backwards. Why do we have to move backwards? Because we are asked about what is the project value as of time 0. So what is, put differently, what is the present value of the project, right? And the present value is not only the cost, or is not only comprising of, well, what our initial costs are, but also a function of what the revenues in the subsequent time periods are. So this is a question of discounting, as you correctly said. So let's go back here to our discounting slide, right? So in order to calculate for a certain monetary amount X, the present value at time 0, right? We would have to do the following. We had to, and recall again, we need to take a look, how many steps do we have to take, right? When we start at period 0, and suppose we have already a payment in period 0, how many steps would we take then if we are considering a cash flow which takes time in period 0? Well, if we are in period 0 and we stay in period 0, we have 0 steps to take, right? So n, which would indicate the number of steps we have to take, is equal to 0. And anything to the power of 0 is equal to 1. So, well, the present value of our payment or our cash flow, which is presently taking place, is, well, the payment at point 0, right? So when we now take a look at our initial example, well, the present value of our minus 1,500, which we have to invest today, is, well, minus 1,500, because that's what we invest today in our project. Now, the 500, we obtain them in period T1. The interest rate is 12%. How many steps do we have to take from period 0 to period 1? Well, how many steps? 1 step only, exactly. So what would be the present value of the 500 when we have an interest rate of 12% and we are walking 1 step? Well, we have 500, that would be the monetary amount we receive in period 1, divided by 1 plus 0.12, which is the 12%, to the power of 1, right? So that would be then our present value of the 500 when we discount by 1 period in order to get the present value of the 500. What would be the present value of the 1,200, meaning the cash flow we obtain in period 2 as referenced to period 0, meaning our present period? how would we calculate the present value of the 1,300 if we have 12% interest? And how many steps to go? Well, 2 steps to go, right? So here we would have to go 2 steps. So what would be the present value of the 1,300 paid in period T2? Well, it would be the respective amount divided by 1 plus 0.12 to the power of 2. Right? That would be the present value of the 1,300. And what would be the present value of the 2,000? Well, if it's getting boring for you, that's a good sign. That means you're starting to understand, or you're understanding, and it should also not get lost from your long-term memory. That's my goal, right? So as soon as you finally say, okay, we got it, that's a good sign for me, and which makes also your preparation for the exam much easier. Well, the present value of the 2,000, which are obtained in period T3, would be 2,000 divided by 1 plus 0.12, which is the interest rate, to the power of 3. Right? And then the present value of the total stream of cash flows would then be the present value of the minus 1,500 plus the present value of the 500 discounted by 1 period plus the present value of the 1,300 discounted by 2 periods, plus the 2,000, plus the present value of the 2,000 discounted by 3 periods. And what we did here was, again, we started with this reference time approach. So we basically took for each of the period the reference time and then went back to the present value in order to calculate this present value of each respective cash flow component. By analogy to what we've done in context of compounding, you could also conduct here a sequential approach, meaning you could start from the 2,000, discount these 2,000 by 1 period, which would give you here an amount which is slightly bigger or higher, bigger or lower than the 2,000. If I discount the 2,000 by 1 period, would I get then something which is higher or lower than 2,000, given that I have an interest rate of 12%? This be higher or lower than 2,000? If I discount the 2,000 here from period 3 to period 2. Yeah, I'm reading in the chat. Lower, right? I mean, the present value of, or not the present value, the value of the 2,000 discounted from period 3 to period 2 would give me something which is slightly lower than 2,000. Yeah. And then this value, which is slightly lower than 2,000, 1,900 something, I would add with the 1,300. Yeah. And then the sum of these two streams, meaning the 1,900 plus the 1,300, I would then discount by 1 period. And then the resulting numerical value, I would add with the 500 and then discount the sum of these, of this total sum by 1 period. And then I would obtain the sum of those sequentially discounted cash flows and then subtract the 1,500. Those I do not have to additionally discount because they're already in time t equals 0. And by analogy to before, what is important and summarized here on this slide is that irrespective, if you follow this, what I just showed you, sequential approach, meaning discounting each cash flow either, or in case of discounting, by discounting period by period and adding the respective sums and then continuing to discount for another period and so forth, or vice versa, the reference time approach where you conduct for each of the cash flows the whole discounting in one step, and this for each of those cash flows, irrespective of which approach you choose. This is something you could recheck by yourself. Both approaches will give you the same, meaning identical result. I mean, in the end, it's math, and irrespective how you discount or how you compound, this will give you the same result. Let me tell you a little bit more about terminology. So when we talk about future value, I mean, this term future value might be a little confusing or imprecise. Therefore, when we will talk about cash flows, you can have basically, or we will use the following terminology. Present value, as already mentioned before, like present value standing also for PV analysis, present value analysis. Well, where you're analyzing the value found at the reference time t equals 0. T equals 0 would refer to today. T equals 0 means today. Whilst time t value approach would basically tell you, okay, what is if we analyze a cash flow at a particular point in time t, right? And when this time t is equal to 0, we would refer to it as a present value analysis. And otherwise, we could perform a time t value analysis, right? This makes terminology a little more specific. So please recall these two terminologies. Now, after we've conducted or discussed so many, well, like individual discounting, compounding analysis, and also after having analyzed like first projects in terms of their cash flows, the one with only positive payments because you basically deposited some money, the other one with also a negative payment, yeah, which reflected like your initial cost or initial, upfront investment, which is negative that you had to conduct before positive cash flows got in. We will now discuss some more, some special forms of cash flows, which you will in future be confronted with more often, right? In particular, when you're also in banking and finance, what you will hear about now is terminologies that you should be familiar with, right? And they basically depict certain forms of cash flow developments, right? With the specifics I'm going to show you, and also with the way how you would have to calculate them, the formula. And the first one of those is referred to as a so-called annuity. What is an annuity? Well, we're still talking about cash flows, and an annuity is defined as a stream of cash flows arriving at a regular interval over a specified time period. Yeah, you have a stream of cash flows arriving at regular interval over a specified time period. One form of annuity is a constant annuity. And recall here is our timeline. So we move to the right into the future as beforehand. We start at time t. And then t plus 1, t plus 2, t plus 3, t plus 4, t plus n. These are the time periods considered. Apparently, we start in time t. We end in time t plus n. That's the specified period of time. And in each of those time periods, we would obtain, there would arrive, to put it more neutral, a constant payment or a constant cash flow in the amount of C. So this is the characteristic of a constant annuity. So if you were asked, what is a constant annuity? You need to know it's a stream of specified number, meaning the period n, of equal cash flows, all in the amount here as depicted by the amount C, all of them with the equal height. So also the height here is the same. We'll see other examples in which that might differ, but the constant annuity has a stream of specified number of equal cash flows that occur at regular intervals. And now the formula to basically calculate this constant annuity, or put differently, the way you could calculate this constant annuity with the knowledge you have so far would be what? What would you do if I asked you for this time t to calculate what I described here as the time t value, a value found by moving all cash flows to time t and taking the sum? So what if I asked you to calculate the time t value of this constant annuity, which has the constant payments c in period t plus 1, t plus 2, t plus 3, t plus 4, and so forth until t plus n? Given that there is an interest rate, which I didn't specify numerically, but suppose you have one interest rate R, and I'm asking you to calculate the time t value where from time t plus 1 onwards, you receive these constant payments. Well, the way which you should know by now, or the way you could apply this formula, or the way you could tackle this challenge, so to speak, could be the following. In analogy to what we've done basically in the last example, right? We had here this the first payment in period t plus t equal 1, where we said the present value of this payment is, well, we discount this 500 by 1 divided by the corresponding interest rate. And for the second period, we divided 1,300 by the interest rate to the power of 2 because we take 2 steps and so forth. Here, we could do the same thing for the constant annuity. We could theoretically say, in order to calculate the time t value, because here we look at time t, in order to calculate the time t value of this constant annuity, one way could be to say, well, I take the first payment c, and in order to calculate the time t value, which is 1 period beforehand, I could say the time t value of this constant payment would be c divided by 1 plus r, right? Because I discount this constant payment by 1 period. So far, so good? Understood? Or is there a question? Is this clear? So this would be how I calculate the present or the time t value of this first constant payment. I apply exactly what we know so far. Again, is this clear? If not, then please write in the chat. Otherwise, I will assume that this is clear. Okay, as I do not see anything in the chat, I assume that this is clear. Otherwise, really clear. Okay, otherwise, really feel free to speak up. The same thing I could do then for the second payment. So how would I get the time t value for the constant payment c of the same height as the payment in the first period? How would I get the time t value of this second component? It would be c divided by 1 plus r. Is this everything, or would I have to do something else? 1 plus r, c divided by 1 plus r, and then to the power of 2, exactly. Well, and the same logic you could apply for the third one. What is the time t value of the payment of c here for the third period? Well, it would be c divided by 1 plus r to the power of 3. Next payment, c divided by 1 plus r to the power of 2. I would do this for all these payments until the last one, which is in period t plus n. And here, for the last payment, it would be, just to make it complete, it would be c divided by 1 plus r to the power of n. And when you make the sum over all these payments, it's a lot of fractions, right? It's c divided by 1 plus r plus c divided by 1 plus r to the power of 2 plus c divided by 1 plus r to the power of 3 plus c divided by 1 plus r to the power of 4 plus all the other ones plus c divided by 1 plus r to the power of n. It's quite a big, quite a long equation. I mean, depending on how long n is, right? I mean, maybe you could argue if I already have 3, if I have an annuity of duration, a 3-period annuity, a 3-period constant annuity, then you could still write that down. But as soon as you have maybe a 200 end period constant annuity, I mean, there's a lot of things to write down, right? So why am I saying this? I'm saying this because through mathematical methods, you can show, this is not anything we're going to prove here or derive, but you can basically show that this constant annuity, which you could theoretically solve in the way I just described with all these sums of the fractions of discount factors for the constant component, you can simplify this equation, which we are not going to prove, but you would have to believe me as of now, or maybe those who are more interested into the mathematical background can try to derive it themselves. But what you can show is that a constant annuity with a finite payment in a period n, the value or the formula to calculate this time t value of this constant annuity does not have to be done in this, well, complicated way. And with complicated, I mean, well, as soon as the number of constant payments becomes very, very frequent, and then you would have to add many of those fractions I just described. But there is a formula which does this more easily. And this is summarized here. So the way to calculate the time t value of the constant annuity would be to take the constant payment, which is constant over all periods, right? You always obtain C. Multiply it by 1 divided by the interest rate. You would always obtain the same interest rate. That's an underlying assumption. And then multiply it by this factor, 1 minus 1 divided by 1 plus r to the power of n, where n is standing for the last period where this constant payment occurs. So long story short, I wanted to basically here introduce to you one standard cash flow payment scheme, which is the constant annuity in a finite horizon with n periods. And I wanted to highlight to you that there are ways for those standard ways or for those standard schemes here, the constant annuity, to efficiently calculate the time t value of this cash flow without having to write down each individual fraction as I indicated to you in the beginning. So you do not have to write down c divided by 1 plus r plus c divided by 1 plus r to the power of 2 plus c divided by 1 plus r to the power of 3 and so forth, but you rather can utilize the formula which is established for a time t annuity, constant annuity, as described here in this formula. So you save yourself a lot of time. Think of n being, as I said, equal to, for instance, 200. If you wouldn't be able, or if it wasn't able mathematically to simplify it the way one can do it, you would have to write down here the 200 fractions as a sum. Long equation and lots of room to make mistakes, right? I mean, there is one typo, then everything is wrong. Here, however, you have total numbers, very few numbers to plug in, and the room to make mistakes is much lower, right? So that's the takeaway from this slide, that for certain standard cash flow schemes, one can simplify the world and make it more easy in terms of calculations. And as I said, those annuities, they might occur in reality, not only from the perspective of investment projects, but also in, for instance, when you have a mortgage, you buy a house and you might have a mortgage contract, which has the form of a constant annuity, meaning your monthly payments follow this constant scheme. And then you're also asking yourself, okay, what is the present value of the mortgage given that you have this initial investment and then the repayments? What is the quality of those mortgages? So these are standard terms to be used. And therefore, in different contexts, not only in corporate finance, but also in banking and so forth, you might come across those terms. And it should be familiar to you, or this term of an annuity should be familiar to you. That was a constant annuity with, well, and here are more exercises which one can conduct here based on also the APR, which we discussed. Now, given that we have also other payment schemes we should go through, I'm now going to focus on the next cash flow scheme, so to speak. So we started with the constant annuity, having constant payments over time over a finite time horizon. But beyond this, there might be also a growing annuity. Growing annuity, right? Also over certain amounts of time, specified number of cash flows. And the difference, as the name already indicates, is, well, you start in the first period with this constant payment C. However, in the next period, this payment C is increasing by the factor, by the growing rate G. So in the first period, you obtain a cash flow C, and then in the next period, you obtain C times 1 plus, well, a growing factor, and this growing factor might be, I don't know, 5%. So you would receive 1.05 times C. And in the next period, because it's constantly growing, you would receive 1.05 to the power of 2 times C. So even a higher payment. So as you can see here, those arrows become bigger over time, meaning you have a growing annuity. So in the specified periods, you would obtain the payments, but the payments are increasing over time. Importantly, in time t, you do not receive a payment, but then as it was in a constant annuity, in time t, you didn't receive a payment, but then from t plus 1, you receive a payment. And well, again, one way to calculate the time t value of this growing value or growing annuity would be what? What would be one way to calculate the growing annuity of this, in our case, 6-period growing annuity? How could you do this? What would be one way to do this?
We can calculate each period individually, like t plus
Exactly.
1.
Absolutely, absolutely. So we could do the same thing as we did today multiple times already. So we could start with each period individually. We could say, what is the time t value of our first cash flow from this growing annuity? This would be C divided by 1 plus R. What is the payment? What is the time t value of the second, of the cash flow from the second period? Well, it would be C times 1 plus G divided by 1 plus R to the power of 2, because we go down 2 steps. What is the present value of, or what is the time t value? Sorry, what is the time t value of the third payment, which is C times 1 plus G to the power of 2? Well, it would be C times 1 plus G to the power of 2 divided by 1 plus R to the power of 3. And so forth. For the fourth one, it would be C times 1 plus G to the power of 3 divided by 1 plus R to the power of 4, and so forth. So we could apply the same methods as we learned, but also here, just notice that also here there is a simpler way to do it, a formula which we're not going to prove that it's true, but a formula which exists in order to also calculate growing annuity values, time t values. And this would be C times 1 plus R minus G. R is the interest rate, G is the growth rate. Implicitly, we will assume that the growth rate cannot be bigger than R. So we will assume, or it's assumed that the interest rate is bigger than the growing rate of the cash payments. And then times this factor as you see here. So you still see the components to calculate the growing annuity value are as before, meaning we need an information on the constant starting cash flow, then the growing rate for each period regarding this constant starting cash flow C, then an information about the interest rate, and lastly, the information about the number of periods this growing annuity is running for, right? Good, so far so good. Apart from these constant and growing constant annuities with constant rates over a fixed number of time, and apart from this growing annuity with constant but growing payments over time over a specified finite number of periods, there is also a so-called perpetuity, right? And in contrast to these annuities, which we've discussed, perpetuities, as their name already indicate, are defined as a stream of cash flows that occurs at regular intervals, so in the same way as with annuities, and make payments not over a finite time of periods, of n periods, but forever. So that's the crucial distinction. So if someone asks you, okay, what's the distinction here? Forever. Perpetuity gives you those cash flows forever. So recall, constant annuity, we had constant number of payments over a specified number of times, giving us this annuity value formula. Now, constant perpetuity looks quite similar as the looks quite similar as compared to the constant annuity, but the difference is there is no end. You know, there is no ending period. These payments go on forever. Constant perpetuity. Well, and I would like to see you to try to calculate this constant perpetuity with the way we started calculating time t values, right? I mean, recall for the constant annuity, we said, okay, let's calculate. One way to do it is to do it in our standard way, to say c divided by 1 plus r plus c divided by 1 plus r to the power of 2 plus c divided by 1 plus r to the power of 3 plus c divided by 1 plus r to the power of 4 plus blah, 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 blah. Let's say you have 199 times you did it correctly, and this is a constant annuity over 200 periods. The last one would be c divided by 1 plus r to the power of 200. Okay, lots of manual work, but possible to be conducted, right? If we are now in the context of a constant perpetuity, I mean, you would never finish this task, right? You would reach period n, but then there is always the next period because it's a constant perpetuity. It goes on forever. And here I'm not going to derive mathematically how this can be solved. I mean, this is like related to those limit mathematical operations. You would basically increase the number of payments to infinity. So n would go to infinity. And when you do this, you apply the limit to this annuity value formula, you would end up, and this is something we're going to see a little later in more detail, but I just want to give you a heads up that the value of the constant perpetuity, the time t value of the constant perpetuity, breaks down to the very, very simple formula c divided by r. So something which, based on these standard procedures where you would apply c divided by 1 plus r plus c divided by 1 plus r to the power of 2, c divided by 1 plus r to the power of 3, and so forth. So a challenge which you cannot succeed to conduct in this infinite context if you apply this really period by period approach. When you have as can be shown mathematically, breaks down to simply saying, well, if I have this constant payments over time forever in the amount of c with interest rate r being present, then the time t value of this constant perpetuity is c divided by r. So a very easy and light formula, right? So this should also be a takeaway for you that, well, you now are equipped with a tool that allows you to calculate for a perpetually, infinitely ongoing cash flow stream to calculate its time t value by simply knowing the amount of the constant payment and the interest rate present currently at the market. So quite a powerful equation, I would say. Yeah. So you see that in the course of today's lectures, we moved from calculating cash flows from one, or by starting calculating a cash flow for one period, or moving it one period ahead. Here, when we started for here, we started from what is the value of $1 after one period, or what is the value of $1 after two periods, compounding context, or from by discounting, if I want to have $1 in one period, how much do I need now? So from this very, very easy examples, or easy as of now, right? I mean, we're in the learning process. Now you're able to calculate the time t value of an infinite cash flow, right? This is quite something. And you could respond to questions such as, what is the present value of a perpetuity paying 100 per year at a discount rate of 12%? Yeah. Well, you could simply apply C 100 divided by 0.12, and you would get the perpetuity value. What is the present value of a perpetuity paying 20 per month at a discount rate of 15% APR? Recall, here you have the payment per month, 50% APR. You have monthly payments. Therefore, in order to get the monthly interest rate, you would have to calculate, as we've done before, 15 divided by 12. So 1.125%. And then with this 1.125%, you could calculate the perpetuity value by setting 20 divided by the interest rate 1.125. So you can deal with such problems already. And by analogy to the, to the constant annuity and the growing annuity, where the distinction was, well, constant annuity had constant payments, well, but finitely, and the growing annuity had growing payments by the growing factor G, also in a finite horizon. Now, by analogy, we have, well, a constant perpetuity, which has constant payments over infinite time horizon. And a growing perpetuity has, well, constant but growing regular payments based on these initial payments C, but then growing and continuing to grow by this factor G in the first period, and then 1 plus G to the, or 1 plus G in the first period, then 1 plus G to the power of 2 in the second, or in the third period, and so forth. But in contrast to the growing annuity, here the growth never stops, right? Because these payments go on forever. Again, if we applied our standard ways to deal with it, well, this would be kind of a lost challenge, right? We cannot go back and say, well, in order to calculate the present value, it's C divided by 1 plus R, C plus 1 plus G divided by 1 plus R to the power of 2, and so forth, because, well, infinite horizon, you will calculate all your life and never find the right solution. But also here, it can be shown mathematically. The growing perpetually value breaks down to a very simple formula. When n goes to infinity, meaning when the number of periods go to infinity, the formula to calculate the growing perpetuity value breaks down to the formula C divided by R minus G. So when you know the starting point of the constant payments, when you're being told, okay, we have a growing perpetuity, which pays initially a constant payment C, has a growing rate G, and has an interest rate R, then you only plug them into this formula to calculate the growing perpetuity value. So you are not only able to calculate the time t value of a constant perpetuity with the formula C divided by R, but also to calculate the growing perpetuity with the formula C divided by R minus G. Great. Good. Some additional infos. Well, when using these formulas, be sure that the discount rate is positive. So these are like underlying assumptions. We will assume the interest rates are positive. So in those atypical times of negative interest rates, we would run into problems. So these formulas assume that it's positive. For perpetuities, as I mentioned already, G must be less than the discount rate. Yeah, so G must be less than the discount rate. Otherwise, we'll also run into problems of calculating growing annuities. And as I already mentioned before, the formulas give the value at time t when the first cash flow is received at time t plus 1. So just to emphasize this again, when we were dealing with constant annuities, the formula we derived assumed that in time t there is no payment, it starts at t plus 1. When we were dealing with growing annuities, we assumed the first payment is taking place at time t plus 1 and in t0 there is none. When talking about constant perpetuities, we were dealing with here, T0, there was nothing, and the first payment is in in T plus 1. And the same with growing perpetuities. We assumed in time T, there is no payment, and the first payment is in period T plus 1. Now, we've seen these 4 formulas. I'm jumping a little bit, but we started with the constant annuity. This was our formula. We had then our growing annuity. This was our formula. We had our constant perpetuity. This was our very easy formula. And we had our growing perpetuity, which was our also very easy looking formula. We can bring all these formulas together here on this sheet. So believe me, trust me that the constant annuity formula is the one which you can find in one of the preceding sheets. The growing annuity formula is the formula I also showed you a second ago. The constant perpetuity formula, you might recall, it was C divided by R, simply depicted here. And the growing perpetuity formula, given that it was also only comprising of these 3 components, you might also recall. And now I want to just show you that all of these formulas are, well, connected with each other, or you can see that they are basically, it's not like they're, in the end, it's mathematics, and you can then play around with different growth rates, with different amounts of periods. And if you do so, you will see that there is a general formula, and from this general formula, you can derive all the other formulas. And the most general formula is the one from the growing annuity. Why is that? The growing annuity allows for what? It allows for growing payments over time, for growing cash flows over time, and it allows for an infinite time horizon. No, that's the constant perpetuity. Sorry, the constant perpetuity allows for the growing perpetuity allows for infinite horizons, and it allows for growing payments. But let's start now with a case in which, from a growing annuity, we have a finite horizon, but which allows, as the name indicates, for growing payments over time. Right? The formula we see here, and which was also included, where was it? Was included here. This is the same formula from the growing annuity slide. As I said, we are not going to derive and prove that this formula is the case. So this is somehow given to you. But once we have this formula from the growing annuity, if we increase n to infinity, we move from the growing annuity, which was characterized by a finite set of payments. So if n increases to infinity, and recall what we said, G must be lower than R, than the discount rate R. If n moves to infinity, what happens to this fraction? If n moves to infinity, 1 plus G divided by 1 plus R, what happens? Well, G is smaller than R. So the denominator is bigger than the nominator. If the nominator is smaller than the denominator, this whole term will be smaller than 1, right? Something smaller than 1 to the power of infinity will go to what? 0, exactly. So if n increases to infinity, while G being smaller than R, this whole term will disappear, right? As n goes to infinity. If those whole term disappears, what is remaining is 1 is basically, is this. Well, and this, what is highlighted here is nothing else than what you see here. It's C times R minus G, or C times 1 divided by R minus G. So you can see if from the formula of growing annuities, we let n increase to infinity, the formula from a growing annuity becomes the formula for a growing perpetuity. Makes sense, right? What happens if we now set G equal to 0 from the formula of a growing annuity? Well, when G is equal to 0, we are in which scenario? If there is no growth of cash flows, well, we would be in the case of a constant annuity, right? Growing annuity at growing cash flows. If G is 0, we are in the case of constant annuity if the number of payments is finite. So growing annuity assumed that the amount, or assumes that the number of payments is finite. If G is equal to 0, let's replace this. G becomes equal to 0 here. So 1 minus G to the power of n becomes 1 to the power of n. Well, and 1 to the power of n is always 1. So that's here. And here 1 divided by R minus G. If G is equal to 0, we end up with here R, right? So we can also see that starting from the growing annuity and setting G equal to 0, we get the formula for the constant annuity, right? Well, and now let's say what we've done in the first place was that we showed from the growing annuity the formula for a growing perpetuity. That was our formula for a growing perpetuity. What if we say we still have a perpetuity, but we do not have a growing rate, no G? Well, if G is 0, we move from the growing perpetuity to the constant perpetuity, and the formula becomes not any longer C minus C divided by R minus G, but if G is equal to 0, it becomes C divided by R. That's the one way you could easily obtain the constant perpetuity by applying the growing perpetuity formula and setting G to 0. Alternatively, you could also say, well, let's start from the constant annuity formula. And the difference between the constant annuity formula as compared to the constant perpetuity formula is what? What is the crucial difference between constant annuity and constant perpetuity? Well, the crucial difference is the amount of periods, right? So constant annuity has a finite amount of payments. So if we want to go from constant annuity to constant perpetuity, we need to increase the number of cash flow payments to infinity. So n must go to infinity. If n goes to infinity, what happens to this fraction? We have 1 divided by something which is bigger than 1, because R is positive. So 1 divided by something bigger than 1, it is bigger than 1. Well, is taken to the power of infinity, which means the denominator becomes bigger and bigger and bigger and bigger and bigger. And this whole fraction becomes what? 1 divided, exactly, it becomes 0. So this term would disappear, right? If this term disappears, what remains would be 1 times, or C times 1 divided by R times 1, which is C divided by R. So your takeaway should be that the formulas which we've discussed in context of perpetuities and annuities, well, they can be, or they are derived somehow from each other. Obviously, once you arrived here at the constant perpetuity, it's difficult to get back to the formula of growing annuity, but the growing annuity formula, which has a fixed n and the growing rate included, from here you can basically derive all the other formulas, right? And I think this is also an important takeaway for you, also to recap, understand, and also be able to apply, right? That being said, I would suggest let's take another few minutes of break. That was a good, that's a good